Tonight, we're going to do something most space videos are afraid to do. We're going to take the journey to Alpha Centauri and strip away every comforting abstraction until what's left is just the raw, unfiltered, deeply terrifying reality of what it would actually cost. The star is Alpha Centauri, the nearest one to us. It's sitting there right now in the southern sky, a faint, patient point of light about 25 trillion miles away. And we're going to figure out, step by uncomfortable step, what it would genuinely take to get there. Not just the physics, not just the engineering, but the human reality. What it would mean for the people who attempted it. Because here's what most people don't realize when they first hear about this. The journey to Alpha Centauri is not just hard. It's not a matter of building a bigger rocket or finding better fuel or waiting for the right political moment. It is something categorically, qualitatively more extreme than that. The journey to our nearest stellar neighbor would be one of the most terrifying undertakings in the entire history of our species. And by the end of tonight, you're going to understand exactly why. Not in a vague, this sounds difficult kind of way. In a, this would break almost everything we are kind of way. If you love exploring the deep end of space and what it actually means to be human in a universe this big, take a second to like and subscribe. It helps this channel more than you know. Now, let's go. Let's start with what you probably already think you know about Alpha Centauri. You've heard it's the closest star. That's almost true, but not quite. Alpha Centauri is actually a system of 3 stars bound together by gravity, located about 4.37 light-years from us. The 2 largest, Alpha Centauri A and Alpha Centauri B, are both similar to our own Sun. They orbit each other at a distance comparable to the distance between our Sun and Uranus, taking about 80 years to complete one full cycle. And then there's the third one, Proxima Centauri, a dim little red dwarf that orbits both of the others from so far away that one of its years lasts somewhere between 500,000 and 1,000,000 of ours. Proxima is the actual closest star to Earth, 4.24 light-years away. The name comes from Latin. It means nearest, which is basically astronomers saying, out of everything in this incomprehensible universe, this is the one we can get to first. In 2016, astronomers discovered something that changed this whole conversation. A planet orbiting Proxima Centauri. They named it Proxima Centauri b. It's roughly Earth-sized, it's rocky, and it sits in the habitable zone, the narrow band around a star where temperatures could allow liquid water on a planet's surface. Not guaranteed, but possible. And that possibility is enormous, because suddenly we weren't just talking about visiting another star, we were potentially talking about visiting another world. One where something could be alive, or could have been alive, or could one day support life from Earth. You can understand why the scientific community got excited. It changed the question from, why would we go, to, how do we get there? But before we get swept up in that excitement, we need to sit with what 4.24 light-years actually means in practical human terms. Because this number sounds almost manageable until you do the math. A light-year is the distance light travels in 1 year. Light moves at 186,000 miles per second, every second. To give you a sense of that speed, light could circle the entire Earth more than 7 times before you could blink. In a single year, traveling at that pace, light covers about 5.88 trillion miles. Proxima Centauri is 4.24 of those years away. That's about 25 trillion miles, 41 trillion kilometers. When you look at it through a telescope tonight, you're not seeing it as it is right now. You're seeing it as it was 4 years and 3 months ago. The light that hits your eye left that star over 4 years before this moment. The star you're looking at is a time-delayed image, a postcard from the past. So, if light takes 4.24 years to make the crossing, how long would it take us? Here's where things get uncomfortable. The fastest spacecraft humanity has ever built is the Parker Solar Probe, launched in 2018. At its peak velocity, during its closest passes around the Sun, it reaches about 430,000 miles per hour. That's genuinely extraordinary by any normal human standard. At that speed, you could get from New York to Los Angeles in about 6 seconds. You could lap the entire Earth in less than a minute. If the Parker Solar Probe were pointed at Proxima Centauri, which it isn't, it would take about 6,700 years to get there. Think about that for a moment. 6,700 years. The entire span of recorded human civilization is roughly 5,000 years. Our fastest machine would need longer than that, longer than everything from ancient Sumer to right now. And then another 1,700 years on top of that, and that's the first terrifying thing about this journey. Not that it's difficult, that our best current technology isn't even in the right conversation. And even that assumes it could maintain its speed, which it can't. The Parker Solar Probe reaches its peak velocity by falling toward the Sun and harvesting gravitational energy, like a cosmic slingshot. Out in interstellar space, far from any massive body, there's nothing to fall toward. It would slow down continuously. You'd need constant propulsion to hold your speed, and constant propulsion means fuel, and fuel is heavy, and heavy ships need more fuel to push them, and that extra fuel makes them even heavier, and you need more fuel still. Rocket engineers call this the tyranny of the rocket equation. It's one of the most fundamental constraints in spaceflight, and it has no elegant solution, only increasingly painful trade-offs. So if we're serious about getting humans to Alpha Centauri within a human lifetime, we need to reach at least 10% of the speed of light, about 67 million miles per hour. That is 155 times faster than our fastest machine at its peak. Nothing we've ever built comes close to that. But before you decide that means it's impossible, let's talk about what the options actually are. Because there are serious candidates. Every one of them has serious problems. And working through those problems tells you something important about just how hard this really is. Before we go further, if you're finding this as fascinating and unsettling as I am, take a second to like the video. It costs you nothing, and it helps this channel reach people who think about things the way you do. Let's keep going. Let's start with what we use right now. Chemical rockets. The engines that put humans on the moon, launched the space station, sent probes to the edge of the solar system. The fastest speed ever achieved by a chemical rocket was about 25,000 miles per hour. To reach Alpha Centauri at that speed would take over 100,000 years. Chemical rockets aren't even in the right category, so researchers started thinking bigger. Nuclear pulse propulsion was one of the first serious ideas. In the late 1950s and early 1960s, a classified U.S. program called Project Orion studied this in real depth. The concept sounds completely unhinged until you look at the numbers. You detonate nuclear bombs behind your spacecraft, one after another, rapidly, and you ride the shockwave forward. The ship would carry a massive plate at the rear, called a pusher plate, designed to absorb each explosion and convert it into forward thrust. The math actually worked. Computer models showed this could push a spacecraft to several percent of the speed of light. The physics were solid. The engineering was horrifying but theoretically possible. The problem was everything else. You'd need thousands of nuclear warheads as fuel. Launching from Earth would scatter radioactive fallout into the atmosphere. And the 1963 Partial Nuclear Test Ban Treaty prohibits nuclear detonations in space. Project Orion died not because the physics failed, but because the world it would require doesn't exist. Fusion propulsion is more elegant. The sun runs on fusion. It takes hydrogen atoms and squeezes them together under enormous pressure until they fuse into helium. releasing vast amounts of energy. A fusion drive could theoretically push a spacecraft to 10 to 20% of the speed of light. That would get us to Proxima Centauri in 20 to 40 years. Now we're talking. The problem is that after more than 70 years of research and billions of dollars of investment, we still haven't achieved net positive fusion, a controlled reaction that produces more energy than it consumes. We're closer than ever, but even the most optimistic timelines put a practical fusion rocket decades away. Antimatter propulsion takes it to the physical limit. When matter and antimatter meet, they annihilate completely. Every particle converts entirely into energy. The efficiency is 100%. Nothing in physics comes close to that. A few kilograms of antimatter could theoretically push a large spacecraft to a significant fraction of the speed of light. The problem is production. The total amount of antimatter ever created on Earth by every accelerator ever built would barely power a light bulb for a few minutes. To fuel an interstellar mission, you'd need kilograms, and storing it is its own nightmare. Antimatter can't touch ordinary matter without immediately annihilating. One tiny power failure in the containment system, one microscopic alignment error, and your fuel supply explodes with the force of a nuclear weapon inside your ship. Solar sails are elegant in concept. Light carries momentum. Photons bouncing off a reflective surface push it gently forward. Build the sail large enough, light enough, and the pressure of sunlight can accelerate you indefinitely. The problem is sunlight weakens rapidly with distance. By the time you're past Mars, meaningful acceleration is essentially gone. Which brings us to the most promising near-term idea anyone has actually funded: laser propulsion. Instead of sunlight, you build a massive laser array on Earth or in orbit and blast a tiny sail with concentrated light. The Breakthrough Starshot initiative, announced in 2016, proposes exactly this. The spacecraft would weigh about a gram. The sail would be a few meters across. The laser array would need around 100 gigawatts of power. That's the output of 100 large power plants, all focused on a target the size of your thumbnail that's already accelerating away at thousands of kilometers per second. At 20% of the speed of light, such a probe would reach Alpha Centauri in about 20 years. But here's the thing, it can't slow down. It screams through the Alpha Centauri system at 20% of light speed, has a few hours to observe and transmit, and then it's gone. Off into the dark between galaxies. Forever. And it's not sending humans, not even close. For a crewed mission, we need propulsion technology that doesn't yet exist. Let's be honest about that. And that honesty is terrifying, because it means everything that follows, every calculation about crew life and ship design and psychological survival, is built on a foundation we haven't constructed yet. We're planning the most extreme journey in human history using an engine we don't have. But let's think through what happens when we do. Let's say a future generation solves the propulsion problem. They push a crewed spacecraft to 10% of the speed of light. At that velocity, the trip to Proxima Centauri takes about 42 years. One way, 42 years. If you leave Earth at 30 years old, you arrive at 72. Your entire adult life spent on the ship, every decade of your most capable years, your career, your relationships, your health declining, all of it inside a metal world between the stars. That right there, before we even get to the radiation or the isolation or the catastrophic failure scenarios, that alone is terrifying, and we're just getting started. Now let's figure out what those 42 years actually look like. The spacecraft would need to be enormous, not just in the sense of a larger rocket. A complete, self-contained world, living quarters, workspaces, medical facilities capable of handling anything from a broken bone to open-heart surgery to end-of-life care. Food production, water recycling, power generation. manufacturing capability for spare parts, recreational spaces because a crew that can't maintain mental health cannot complete the mission. Everything required to sustain human life for 4 decades has to either be on board from the start or be producible from what's available. There are no resupply missions, no emergency deliveries, no calling for help. When that airlock closes at launch, what's inside is all there is. For the rest of their lives. How many people? Too few, and you have real problems, not enough expertise to cover every possible emergency. If your only physician dies at year 20, that's a catastrophe with no external solution. Too many, and the ship needs to carry more of everything, which makes it heavier, which makes the propulsion problem harder. Most serious mission studies suggest somewhere between 50 and 150 people for a voyage of this length. Every single one of them would need to be an expert in multiple fields. Doctor and engineer, biologist and psychologist, farmer and physicist. The margins for incompetence are essentially zero. Now let's talk about what the environment would actually do to those people. 42 years of weightlessness would be catastrophic for the human body. Bone loss, muscle wasting, cardiovascular deconditioning, vision damage. Astronauts on the ISS exercise 2 hours a day and still show significant deterioration after 6 months. For a 42-year voyage, the crew would need artificial gravity. The most practical approach is rotation. Spin a section of the ship and centrifugal force mimics gravity. But to keep the disorienting effects tolerable, the rotating section needs a radius of at least 100 meters. That's a habitat the size of a city block, spinning continuously, its bearings maintained by a crew who can't order replacement parts from anywhere. Power comes from nuclear reactors, multiple reactors for redundancy, because a single failure in interstellar space can't be allowed to end the mission. Those reactors generate heat, and in space there's no air to carry it away. You need massive radiators extending from the hull to bleed energy into the void. The bigger your reactors, the bigger the radiators. Radiators are heavy and exposed. A debris strike could shear one off, and suddenly you have a thermal crisis that has to be solved with whatever is on the ship. Food and water are subject to a tyranny of their own. You can't carry 42 years of food for 100 people. The mass alone would be prohibitive. You need a closed ecological loop, hydroponic gardens under artificial light, aquaculture producing fish or algae, composting returning organic waste to growing medium, water recycling capturing moisture from breath, perspiration, and urine, purifying it and putting it back into circulation with near-perfect efficiency. The ISS recycles about 93% of its water. For this mission, you'd need to push well past that, because even a 1% daily loss compounds into catastrophe over 42 years. Every crop failure is an emergency. Every component of the food system needs a backup. The crew would know every meal by heart within a few years. Food stops being something you look forward to, becomes fuel. Medical care needs to cover the full range of human health across 4 decades with no outside support. Multiple physicians. Surgical capability. Pharmaceutical stockpiles. If someone develops appendicitis, the ship's doctors handle it. If someone needs cardiac surgery, the ship's doctors handle it. With what's on board. No specialists, no hospital within 25 trillion miles. And then there's the radiation. In interstellar space, far from Earth's protective magnetic field and atmosphere, the crew would be continuously bathed in galactic cosmic rays. High-energy particles accelerated to near light speed by distant supernovae and black hole environments. Some of these particles are so energetic they punch through almost anything we could practically put on a spacecraft. Over 42 years of cumulative exposure, the crew would absorb radiation doses far beyond what's considered the lifetime limit for professional astronauts. Cancer rates elevated, cataracts, cardiovascular effects, potential neurological damage. Every volunteer who boards that ship accepts this. It's not a solvable problem with current technology, it's a cost you pay for going. And that's terrifying in a very specific way, because it means the journey doesn't just risk killing you out there, it's quietly working on killing you the entire time. And space itself isn't empty. Interstellar space contains gas, dust, microscopic particles. At 10% of the speed of light, any particle becomes a weapon. A single milligram of dust carries the kinetic energy of several kilograms of high explosive at that velocity. A pebble hits with the force of a small nuclear weapon. The front of the spacecraft needs heavy shielding. But shielding is mass, and mass is the enemy of every propulsion calculation. There's no clean answer, just trade-offs. Now let's talk about the part that doesn't get enough attention, the human part. Humans were not built to live in metal boxes. We evolved in open environments with weather, seasons, variety, new faces, open horizons. The spacecraft is the opposite of all of that. Same corridors, same rooms, same recycled air, same faces every single day for 42 years. No escape, no option to leave, no ability to take a walk outside. We have some data on what extreme isolation does to people. Antarctic research stations, submarines, the International Space Station. Even in those environments and missions lasting months rather than decades, carefully selected professionals experience depression, anxiety, and interpersonal conflict that escalates far beyond what the circumstances warrant. Small things become enormous in a closed space. The way someone chews their food, a laugh at a certain frequency, someone leaving a cabinet open. In ordinary life, these evaporate. In confinement, they compound over years into something much harder. Now multiply that by 42 and remove any possibility of exit. There's a phenomenon in isolation psychology called third quarter syndrome, the motivational collapse that hits past the halfway point when the excitement is gone and the destination still feels impossibly far. Every long-duration mission encounters it. Cosmonauts, Antarctic teams, submarine crews, all of them show the same dip. Now put that at year 21 of a 42-year journey, 4 light years from the nearest other human being. No rescue coming, no way to pause. You push through or the mission fails. Communication with Earth would start as a minor inconvenience and slowly transform into something closer to existential loneliness. At first, radio signals take minutes to reach Earth, then hours, then days. Within a year, messages take a year to arrive. A reply takes another year to return. By the halfway point of the journey, a single question and answer exchange spans more than 4 years. Think about what that means. You send a message. 4 years later, you get a response. By then, everything has changed. The people who answered have aged. The institutions that replied might have restructured. The context that prompted your question no longer exists. You're not communicating with Earth anymore. You're exchanging letters with a version of Earth that existed years ago. The news from home arrives years stale. Political events, scientific discoveries, personal updates from families left behind. All of it like letters from another era. The crew would be culturally frozen at the moment of departure while Earth keeps moving forward without them. By arrival, the civilization that launched them might be almost unrecognizable. This is isolation at a scale that has no human precedent. Not just separated by distance, separated by time. And that distinction matters because it means even the abstract comfort of feeling connected to home erodes completely. They're not with you. They're in a past you can no longer reach. That's a terrifying kind of alone. And here's something that doesn't get talked about enough. The weight calculation. Technology keeps advancing. From the moment your ship leaves Earth, the engineers left behind are already working on something faster. If fusion propulsion is cracked 20 years into your journey, a second ship could launch and overtake you. It could arrive at Alpha Centauri years before you do. The history you were meant to make, the discoveries you were meant to claim first. All of it handed to people who left after you and traveled faster. Imagine receiving that message. 30 years into your journey, you've given everything. Your youth, your health, your relationships, your entire adult life spent crossing the void. And the radio brings you this. A second mission launched, faster, arrives before you. How do you feel? Angry, betrayed? Proud that humanity found the better path, even if that path made your sacrifice invisible to history. All of it at once. No training prepares you for that. No psychological simulation on Earth can replicate what it would do to a person, and you'd have to carry it for the remaining years of the journey, in the same corridors, with the same faces, still moving in the same direction, because there's nothing else to do. That might be the most quietly terrifying thing in this entire story. Not the radiation, not the debris. The possibility of learning midway through your sacrifice that the sacrifice was for nothing, and having to keep going anyway. Now, who would actually volunteer for this? And here's the thing that always surprises people: there would be volunteers. Real ones. People who understand exactly what they're signing up for and say yes anyway. Some driven by the kind of curiosity that doesn't switch off. The need to actually see what's out there that overrides every other consideration. Some would go because they genuinely believe humanity's survival depends on becoming multistellar before something ends us on Earth. Some would go for legacy, to have their names written into history with a permanence very few lives ever achieve. And some would go because they're running from something, looking for the most complete escape physics permits. Whatever the reason, these people would be giving up everything. Family, friends, the smell of rain, the feeling of wind, seasons, animals, the entire sensory texture of living on a planet, permanently. And they would know this when they walked through that airlock. Imagine you're one of them. You've spent years training for this. You know the ship better than your own apartment. You've been told in clinical language the projected radiation dose you'll accumulate over 42 years, what that likely means for your health, and approximately how it might eventually end your life. You signed the consent form. And then the day comes. You're standing at the airlock. Your family is on a screen somewhere behind you. And you realize that the choice you already technically made becomes real only right now, in this specific second, with their faces on that screen. You walk through. The door closes. And something changes. Something permanent. You've crossed a threshold that has nothing to do with the physical door. You've become a different kind of person than you were on the other side of it. The first months are electric. Everything is new. The rhythm of shifts and meals and exercise, the sight of Earth receding, that blue dot getting smaller, becoming a point of light. And then one day you realize you can't find it anymore. You're looking at the star field on the aft cameras and you genuinely cannot identify which one is the sun. That's the moment most crew members would describe as the one where the reality of the journey lands fully. The moment home disappears, and then comes the routine, year after year of it. Wake, eat, work, exercise, sleep, repeat. The same corridors, the same smell, the same faces. Small frictions that would dissolve in ordinary life calcify in a closed space over years into something much harder. You know exactly how this person laughs. You know what that person does with equipment that quietly drives you out of your mind. You've known these things for 15 years and you'll know them for 27 more, and there is nothing to be done about it. Some crew members will die before arrival. Statistically, across 42 years with a group of 100 people, multiple deaths are near certain. Some from illness. Some from the accumulated effects of radiation. Each death reshapes the crew. The removal of one person from a small, closed community doesn't just create a vacancy, it changes every relationship in that community because every relationship existed partly in the context of that person. The grief is complicated by all the texture of who they were in relation to everyone else. And the mission continues, because it has to. Now let's talk about what happens when something goes catastrophically wrong. Because over 42 years, the probability of at least one serious crisis is near certainty. Picture this: a micrometeorite impact. A particle moving at relativistic speed punches through the forward shielding and breaches a habitat section. The airtight doors slam shut. Alarm screaming. Anyone in that section without a suit has seconds. The crew scrambles to assess the damage. If it's a critical area, life support or reactor monitoring, the entire mission is in jeopardy. Someone has to suit up and go outside, into an interstellar environment where the cosmic ray flux is severe. An extended EVA means a radiation dose that will almost certainly shorten the life of whoever goes out. Someone has to volunteer knowing that, because there is no one else to call. Or imagine a pathogen. Despite every precaution, something makes it aboard. It spreads. The medical team moves fast, but medical resources are finite, and if the pathogen proves resistant to everything the ship's formulary can bring to bear, the decisions that follow have no good options. They have only degrees of terrible, made by the crew alone. Because Earth won't even know this is happening for 2 years. These aren't fantasy scenarios, they're the kinds of events that mission planners take seriously. Because in 42 years, something will go wrong. The terrifying part isn't just that these things could happen, it's that when they do, there is no rescue. No backup plan involving anyone from outside. Just the crew in the dark between stars solving an unsolvable problem with whatever they have, or not solving it. Let's talk about arrival. Because even if the journey goes perfectly, arrival is not the end of the problems. The spacecraft is still moving at 10% of the speed of light. To enter orbit, you have to slow down. Decelerating from that speed requires almost as much energy as accelerating to it. You need twice the propellant budget or an alternative method. Some proposals involve a magnetic sail, a loop of superconducting wire creating drag against the stellar wind. But Proxima Centauri is a red dwarf with a relatively weak stellar wind. Braking this way would take years and requires everything to function perfectly. If you can't slow down, you do a flyby. You scream through the system in hours. Grab what data you can and head off into the permanent dark. All of that journey, all of that sacrifice, for a brief glimpse. Let's say you manage to slow down. You achieve orbit. You start observing Proxima Centauri B up close. What do you see? Proxima Centauri is a red dwarf, about 12% of our sun's mass. Dim, cool, and red. To stay warm enough for liquid water at that low luminosity, the planet orbits about 20 times closer to its star than Earth orbits ours. It completes a full year in about 11 Earth days. At that distance, tidal forces have almost certainly locked the planet into synchronous rotation. One face always toward the star, always daylit, baking. The other face always away, always dark, frozen. Any habitable zone would be a narrow, wind-hammered ring at the boundary between them. And Proxima Centauri is a flare star. It erupts in powerful bursts of X-rays and charged particles, sometimes hundreds of times more intense than anything Earth experiences. A planet this close gets hit by those flares regularly. Without a strong magnetic field, the surface gets sterilized on a schedule. Any life would need to be underground, deep underwater, protected by kilometers of rock or liquid from radiation that would kill surface life quickly and thoroughly. So Proxima Centauri b might not be the welcoming Earth-like world we picture when we let ourselves dream. It might be a radiation-scoured rock with a thin, hostile atmosphere and hurricane-force winds at the only temperate zone. And here's why that's so specifically terrifying. You've spent 42 years getting there. You've given up everything. And the destination might be completely uninhabitable. There's no way to know until you arrive. You're betting your entire life on a world you've only ever seen as a point of light. But even a hostile world changes everything we know. If the planet is entirely barren, that tells us something profound about how rare habitable worlds might be. If there's water somewhere underground or shielded in polar regions, that changes how we think about the ingredients for life in the universe. And if they find something biological, even ancient, even just the fossil chemistry of something that once metabolized, then everything changes, because it means life is not an accident of Earth. It's a tendency of the universe. And if it happened here and at Proxima Centauri, it probably happened billions of times throughout the galaxy. Back on Earth, over those same 42 years, the world would have changed in ways that are hard to fully predict. New technologies, different political landscape. The engineers who designed the ship mostly retired or gone. The politicians who funded it long out of office. The children who watched the launch now middle-aged, with children of their own who have grown up hearing about the crew that's still out there, still traveling. And then, finally, a signal arrives. 4 years old by the time it reaches Earth, but unmistakable, they made it. The reaction would be unlike anything in living memory, because this is real. Humans in another star system. For the first time in the history of life on this planet, something alive that we know of has crossed between stars. And whatever they find changes us. Permanently. Not just scientifically, philosophically. It forces every assumption we've ever made about our place in this universe to be looked at again from the beginning. Now, would you go? Imagine you're offered a position on the crew, the best training Earth can provide. A place in history that will be written about for as long as humans write about anything. But you leave forever. You grow old between stars. You might arrive at a new world, or you might die before you get there. No guarantees. Would you say yes? Some people would answer instantly. The adventure, the legacy, the chance to see what no human has ever seen. Worth any price. Others would refuse. The thought of leaving the sky, the grass, the ocean, the people they love permanently is simply too much to give up. And both answers are completely valid. It's not a test with a right answer. It's a question about what matters most to you. But here's what I keep coming back to. The journey to Alpha Centauri is terrifying. Every single element of it. The distance. The propulsion problem, the decades in confinement, the radiation working on you silently, the debris that could end everything without warning, the destination that might offer nothing. And underneath all of it, the knowledge that no one is coming if something goes wrong. And it's inevitable anyway, not because of some grand cosmic plan, but because we are what we are. Because the drive to cross the next horizon is not something we've ever successfully reasoned ourselves out of. Because there will always be people who look at that faint point of light in the southern sky and find the not knowing more unbearable than the going. The nearest star is 4.24 light-years away, 25 trillion miles of cold, irradiated, particle-filled void. Getting there will demand technology we haven't built, courage we haven't yet tested, and sacrifices most of us can barely imagine. But someday someone will make that journey. And when they do, they'll carry with them every person who ever looked up at the night sky and wondered what's out there. They'll carry that question all the way to another sun. And whatever answer they find will change everything. Thank you for joining me tonight. If this changed the way you see that quiet point of light in the southern sky, please take a second to like this video and subscribe to the channel. It helps more than you know. And the next time you find Alpha Centauri up there, patient and distant and indifferent, remember what you now know lives between here and there. The distance, the silence, the radiation, the decades, the sacrifice, the terrifying, humbling reality of what it would take to cross it. And why we're going to do it anyway. Sleep well tonight. And keep looking up.